Good morning, everyone. So I'm trying to set up a live demo, so let's see how this goes. Maps. We all know maps, right? I have bad news for you. Maps, as we know them, are dead. They are dead because they don't represent anymore the world we live in, the world we navigate in. So many of us were driving here or walking here and so on. And yes, we could see that Alfanga was here, but probably the maps we were following were not representing the world that we were observing. There were construction zones, there were potholes, there were different things that sort of shaped the way we navigate safely to this destination. So maps historically have been developed based on by indexing information in a stable set of coordinates. So we have latitude, longitude, and we index that information in the map. We can have locations, we have points of interest, we have places we want to go. So this is how historically maps have been developed. And we still rely on those maps, we still rely on those systems to develop geospatial data engineering foundations that require some type of location, some type of navigation. So what I'm here to share with you today is how we at Nexon address this challenge and how do we build a different map, a map that is a real-time map that represents what we see and observe in the world in real time. So the goal here is for you to, if you're working with geospatial data, if you're working with large data pipelines, to take some of these tricks that over time we've developed and some of the problems that over time we solved and try to apply to your own problems. So but let me first start by talking about the different types of maps, the different types of layers that come with this new generation of maps. So it all starts with the base map. The same set of coordinates so that we can still understand how to navigate in this new generation of maps. However, there's then new types of information we need to have in that map. So we not only know that this street goes from point A to point B, but we need to understand how many lanes are there, how do we navigate, especially in construction zone and here in Porto, that's changing all the time. So we would require this map to be constantly updated. But still, we get that from Waze and we get that from some other companies. But all in all, every couple of months, every couple of weeks, we require this type of update. However, there are more things changing besides the lanes. There's what we call road furniture. We have the traffic signs, we have the traffic lights, different indications on the street that tell us how we can safely navigate or walk. We have the cones, the drums, all these things that we see now in the streets, in cities like Porto and pretty much everywhere in the world, that are constantly changing, and that requires an even more updated version of the map. Then we have things that are getting closer to real time, things that change on a daily basis or even within minutes and seconds. And that may, for example, be a construction zone or an incident that happens right there. So a car clashed against the other, and now we need to adapt and adjust the way we navigate safely in the maps. Then, of course, when we have all these layers that get updated in real time, we need to understand how people navigate these maps. These behavioral maps is something that changes all the time. It changes within a second. So you're driving, you see a construction zone, you're not counting on it, you're sort of distracted, and all of a sudden you exhibit a different behavior as a pedestrian, as a driver, that will affect everyone around you. And let me share with you a story. So last week I was here in Porto. I was invited for a dinner with a friend. I was going from Porto to Maia. This was in the same day there was this sort of moderate flash flood that we had in Porto, so everything was changing. For those of you who were here, you know what I'm talking about. For those of you who were not here, probably saw on Twitter some footage, well, the real one, where that showed how floods were happening here in Porto. So I didn't know how to get there, so I just added the location in the map, and I was driving, navigating there. The map is quite updated, so it represents real-time traffic. It's updated pretty much every week, so I pretty much trust this map to take me safely from one point A to point B. I was driving safely, I was on some weird roads in Maia and so on, almost getting to the destination, and then I got into a crossroad. What I didn't know is that this would be not only a literal crossroad and a figurative crossroad. So I saw like a little bit of water, and that was fine, so I kept driving, and suddenly I had water halfway in my car. I drive an electric car, so I started thinking, okay, I really hope this is waterproof. So I couldn't go forward. I was able to manage my way out. It took me a couple of minutes. The stress levels increased. And then I routed my way out and so on, and I found my way to the restaurant. Why is this relevant? Because 10 minutes before, that was a fine, super fine street to navigate. After dinner, I actually went there to see, and it was fine. I actually went through it. So it changes all the time. So, and I was following the most accurate map we can get out there in the car. So this is the type of challenge that we have. How do we build these real-time maps? And I want to share here with you is our journey, how the different technical challenges of building these maps at scale were addressed by us. So very quickly, for us, it started with the network. So we have over 700,000 devices out there in the world that are capturing the world as we see it. So these are dash cameras, cameras that you can put in your car that process what you see around you. This is useful, for example, for you to reduce your insurance claims and so on. That's not what matters, but we have a lot of people contributing and crowdsourcing this data that maps the real world. So we can see 94% of all the roads in the United States every month, and we have a number of events that we detect on a daily basis, around 25 million detections that we do. And I'll talk about what are those detections in a second. The thing is, okay, we could go the old way. We upload all the data, we have these very expensive data pipelines, we process the data out of it, and the insights, that's great. However, that would not scale. That would not serve the purpose of building this real-time map. So we had to divide this challenge in 3 different parts. And today, we're going to dive deeper quickly in each one of them. The first one is how we gather this data. The second one is how we index this data. And the third one is how we serve this data to our developers and to our partners. So the first thing was, okay, instead of processing all this data in the cloud, we're going to leverage the existing compute capacity in these cameras to process data. Not only to process data, but also to storage. This way, we will ensure that we don't have a large storage issue of data in the cloud that we need to serve and so on and process. That would be very expensive. So from the get-go, we decided to push and to find ways to design our systems that would leverage this type of compute and storage capability at the edge. So we're going to go through the different processes, different steps, but essentially on your left-hand side, you will have the cameras that run our embedded software, and then we have a combination of both edge and distributed cloud solutions to really sort of divide and push compute to where the data is, being either at the edge or closer to the cloud. Okay, let's start. So gathering data. The first thing is how do we ensure that we, in a cost-effective way, can gather this data from the cameras. And here we followed Google's recipe for doing this. So back in the days, Google did something different some decades ago. That was, instead of us trying to process data and text and so on to extract and classify the types of websites, they actually pushed data labeling to the users. So we follow the exact same process. So instead of us, again, sending the data to the cloud and trying to extract and understand what are the semantics of the real world, we used the computing capabilities in the cameras to do data labeling itself. So the way it works today is that we train our own neural network that we push over the air to these cameras, and we are constantly ensuring that we detect and update this model over the air. So this allows us to define what are the elements that we want to upload from the device to the cloud, therefore, again, pushing computing to the edge and not requiring in the cloud to be constantly updating this. So here, the element that is important is not only the fact that we run a neural network, but the fact that we can update this on a weekly basis. So now you want to detect, I don't know, a new type of traffic sign, then we can do the same. The second aspect is how can we do this cost effectively? Because even though we are detecting stop signs, there are millions of them all over the world. So the second way for us to solve this is to do what we call intelligent data networking. So to decide, okay, is this information really important right now? Yeah, if so, let's upload it over cellular data, so 4G, LTE, or 5G. This is important, but not in real time, so let's send this later on. We probably try to send it over Wi-Fi or any other type of storage. Or, for example, this data might be important, but we will only know, for example, if someone submits a claim in insurance or if someone requires this data. So this deferred upload of data, it was also a mechanism that was really relevant for this. So you have, I guess, different tiers of data that would allow us or allowed us to really scale the data collection aspect. The last, but not the least definitely, is the fact that it's really, really important while designing these systems that you take privacy in consideration as part of your foundation principles to build this data. So for us, in our case, we decided that no data leaves the cameras without being anonymized. And I will show you in a few seconds how this works, but essentially, not only the data of the owner of this camera, but also the data of the people around you. So initially you could say, okay, I will just remove the MAC address and so on in my location, and I'm good. However, we are acquiring images of the world out there, and we will see people on the street. So that, for us, was super important. The license plates, the dashboards, and a number of other elements. So I'll do a live demo, if all goes well, right now to show you how this looks like. Oopsie. Okay. Sim, mas posso ligar. Live demos are always exciting, right? Let me see. Okay. Pode ligar? Okay. Dá para mostrar no ecrã o outro? Ah, não está aparecendo nada? Ok. Yeah, sure. Okay, so live demo postponed, but we'll carry on. All right, so what I was about to show, and I'll try to do it within the time we have left, otherwise I'll show you how you can access all this information. So what I was about to show you is how this is happening in real time. So we have a dashboard called citystream.getnexon.com. You can access, you can register and get access to it. So you will be able to see that we are collecting data in real time, and then when you open images, and I have a couple examples out there, we can see that how this information is gathered at scale. So we'll try to do the demo, but we'll go to the next part. Because what was impressive about this demo is not only the fact that you can see, like, 30 seconds ago, someone detected a new construction zone or a new pothole in Las Vegas or in New York, wherever in the world, but the fact that this happens at scale, and you would see maps of this information flow in real time. And to be able to serve this and to solve this problem, we have to go to the next challenge, which is how do we index data? So let me start by sharing something, a mechanism that is super important. Many of you probably already use it, especially if you use geospatial data, which is Uber's H3 mechanism or indexing mechanism. So it stands for Hexagonal Hierarchical Geospatial Indexing System. And in a nutshell, Uber, the engineers and team, they divided the world in 122 base cells. And these base cells are shaped as hexagons. Hexagons, for those of you who, again, who don't know, are not fascinated by it, they are the most elegant structure that we see a lot in nature, in beehives, and other types of formations, but also for information retrieval. Why? Because, especially when you think about geospatial data, this is the shape, geographical shape, that minimizes information entropy and allows you to have 6 neighbors around you and ensure that you can navigate from one side to the other and do different type of neighboring algorithms. So the key aspects of this is not only the fact that they are shaped by hexagons, but with a 1-bit operation, you can go to the neighbor, one of the 6 neighbors around you. With 2 bits operation, you can go to the second neighbors, and so on and so on. So this is really, really important because, for example, the best way to, or the most elegant way to index this data is not by do a full table search when you're trying to get data, is, okay, I'm here, tell me what's around me. Or I want to go there, tell me the different steps between here and there. And again, you could have different ways of indexing data, and the Uber H3 is exciting because it solved this problem in a very elegant way. The second aspect was that these hexagons are hierarchical. You have different resolutions. So it starts with this resolution 0 base cells, but for example, you have up to 15 resolutions. And if we think into resolution 5, which is again smaller hexagons, we have 2 million hexagons all over the world, and each of them covers an area of 252 square kilometers. For example, if we go into resolution 8, we have 691 million and 300 square meters. So what we see here is actually where we are right now. So we stand in this hexagon. This is the Alfanga, roughly where we should be in. See, that's why I need maps. We are in that building, but here you can understand how this maps the world. But this is not, again, this didn't solve our problem. How do we map road segments, because again, this covers a large area. So that's when we realized, okay, we need to build on top of this. And that's when we entered the Nexagon. So next are hexagons for the, again, super creative. So what we did here is to overlap this H3 formation of the world and then map this with OpenStreetMap segments. This way, we have this structure that not only refers to an hexagon, but can tell us the streets and different type of road segments that we have out there. And this is not only for road segments. You can have pedestrian ways, construction ways. Every type of structure that you have in a map, you can overlay in this type of structure. So what is the foundation mechanism that we have here? Sorry. So the first thing is, in terms of strategy, we decided to, instead of building the index in real time, we built the index offline. So we build this index first, we create to populate our tables, and then we are able to ingest this data. So every single of these Nexagon, we can store images, detections, incidents, near incidents as we had right here, and we can store this in the map so that you can access this in a cost-effective way. So avoiding full table scans and doing this offline index building. The second aspect is the way we built these indexes. So each of these Nexagon is represented again by the H3 resolution, the source ID, and the destination ID. This is also, for us, was important because this became an IPv6 address. So we not only have an index that we can store cost-effectively in the database, but we can also have a map of the world that we can use the different networking protocols to address, either with geo-routing or multicast or geocast, to access this information. So all of this index, all of the world is now addressable by a single IPv6 address. So again, for us, it was important, not because as we have this data in the cloud, we also want to push this data more towards the edge. So now we have this bridge between the data and networking that really allows us to do this at scale. So the next challenge was, now we have all this data, how do we serve this data? And there are two ways, and there's going to be a third way that we're going to expose this data. The first one is that all of this data is exposed as gRPC protobuf and wrapped over HTTP APIs. So you can register in developers.getnexar.com, you go there and you register, and you can build your web applications on top of it. Why we use gRPC is because all this data is relevant for users in the web, but also super relevant for devices and agents out there. So therefore, you can, as your own device and your cameras, you can access the same type of information, and you can push the information to the edge, either in the cloud or closer to where the real-time map is. The second aspect is, of course, now with generative AI, there are new exciting ways to interface with data, so you can also chat with the data. You can ask, give me all the potholes with a lot of water on my destination from Porto to Maya. So this would have probably solved my driving situation last week. And there will be more, because then this is just the beginning, and for us, the next challenge is, okay, we pushed computation close to the data, where data is acquired. Now for us, we want to push computation closer to the data that we already have, the petabytes of data we already have. So that's going to be a new way of serving data, but that's probably for another day. So all of this is important. I mentioned this a couple of slides ago, that, yeah, it's important to do all this, but never compromise on the principles of data privacy. The first one is, as I mentioned, so all the frames are blurred at the edge, so I probably won't be able to show it, but that's what you'll see in the demo. You can go to the website and see it as well, and that's a super important aspect. The second one that is important, especially if you are building geospatial data within IoT devices or IoT networks, is to ensure that also your network footprint is not traceable. So we developed an ITF draft that is currently right now in RFC that uses ephemeral IDs for the devices to identify the network. So, sorry, I need water. So this way, when devices identify the network and they connect, you are not able to use their IP addresses to trace back a given device. And this is relevant because you cannot do this breadcrumbs exercise to really reconstruct someone's location. And then for us, it's important because there's private data, but would we keep all these tenants super separate so that the mapping data is totally separate from the private data from our users? And for us, and just to finish, this is just the beginning. So as we build these maps, we now have this understanding of how the real world is mapped, but we also, for us as human beings, the world and the maps are spatial. We don't only see in 2 dimensions and latitude and longitude. We have this projection in time and in space that now can be built. And for those of you who work in computer vision and are fascinated about this, again, there is a lot of work being developed in this area. So that's it for today. I just shared a couple of tricks here on how you build this index hike. Almost failed, but I really hope that this was something useful for you, especially if you're working with geospatial data and IoT devices. So one final word in the few seconds. So as you probably know, the Nexon team is based in Israel. Many of our friends are now affected by this, and I just want to send a big hope that they're all safe. And that's it. Have a great day. Thank you so much.
Yeah, thanks.
Yeah.
Amazing presentation. I was wondering, so this Nexagon system that you showed, is it open source?
So it's described in the RFC that I mentioned, and our goal is to now then also open source the code that generates and that allows you to interface with this.
But you mentioned that it's possible to go and play with a demo. I guess like it's available on your website.
Yeah, so there's a website, data.nexon.com. You can navigate there to how to interact with this data.
Because one of the questions from Pablo, his company has people running on the street delivering goods, and he was asking about like how to actually do the best, find the best route and answer questions like that, which I think you presented with this hexagon stuff.
Yeah.
So we will not go into details. There is a more upvoted question from Henrik, which is what I also had when listening to the talk. So you mentioned you have dash cameras on cars, and I live in Germany. So in Germany, actually, this is illegal to have dash cams, right? Because like you can accidentally film somebody who has not agreed to be being filmed. And the question from Henrik is like, are there legal implications on using data from these dash cams?
Yeah. So that was what we were supposed to show in the demo, that you cannot, when you're collecting data from the real world, or if you drive a car with camera footage and so on, or you can put your own GoPro in the car, you can store your data for you, but you can never publish this information to the internet, because then you become a data controller and you become liable for this information. For us, even though we could push this sort of responsibility to the end user, we decided to anonymize all this information at the edge. So even if you go to the camera, to the website, you will see all the pedestrians anonymized, so it's not possible to understand what we have in the map. So the only thing we display are items that are relevant for building a map. So the stop signs, the cones, the potholes, but every time that we overlap with something that can be perceived as private information, it's discarded from the entire data set.
And in your talk, there was a slide with the map of the states of the USA. So I guess this is where you mostly operate, right?
So one of the biggest deployments we have is in the US, but as we would see in the demo, we also have a large footprint here in Europe, including here in Porto. There are some cameras, and we were able to see, for example, how bad the weather is today.
Yeah, because I assume in the States, this private information is more like flexible compared to Europe and Germany. So in the States, you can do that.
Yeah, we need to keep, again, privacy is very important for us because we have our engineering team here in Portugal, and this privacy regulation is being updated all the time. So we also want to serve our European customers. So that's why it's super important for us to be compliant with what's considered personal identifiable information, GDPR and CCPA, and all other privacy regulations all over the world.
Okay. So another question. Can you use this data to generate information about, says foot traffic, I think flood traffic or traffic.
Foot traffic?
Foot
traffic. Okay, for example, the density of people that we have in different locations.
Yeah, right.
So yes, we can, because one of the things we detect at the edge is pedestrians, because we need to detect people to be able to anonymize them. So we can count the number of pedestrians that we have in a certain location and measure this to understand and infer what's the density of people in Times Square, what's the density of people we detect in the streets. So again, we need to understand how our sort of deployment is modeled. So these are cameras in cars. So we want to be able to count foot traffic in a given location where a car sees anything, but that's definitely something that we could build with the data.